Hello everyone, I am Dinesh from CSC department A section. This is my engineering chemistry PPT presentation. And the next slide. And my topic is an energy service interface for distributed energy resource. From this topic, we will understand about an energy service interface for distributed energy resource. And that is the topic, an energy service interface for distributed energy resource. Given the communication importance in the modern grid, the communication interface between the grid and any DER has been generalized as an energy services interface ESI. An ESI is a bidirectional service oriented logical interface that supports the secure communication of information between entities inside and entities outside of a customer boundary to facilitate various energy interactions between electrical loads, storage, and generation within customer facilities and external entities. And this is a picture which describes external responsibility, internal responsibility. And the next, an architectural context for ESI. Architecture describes system concepts, structure, and organizing principles. Interoperability drives simplicity of system integration. Example, architecture prescribes layered decomposition coordination framework which defines interface points for interoperability. The ESI concept respects the boundaries of responsibilities at the grid and DER facility interface. Key energy service interface elements. First one, ESI facilitates automated machine-to-machine communications to support business practices. A service-oriented interface defining what is needed when, not how to deliver it. ESI includes functionality, defines services, example, what service is the grid or DER requesting or offering, and what is the performance requirement. Qualify and register for a service, measure and validate performance. ESI can be described by a functional specification focused on messaging, communication conduit between grid and customer sited equipment, does not receive direct control signals nor content control logic. Defined independently of implementation. The implementation details such as data storage, etc. Key question: how someone would spec an ESI in the future and what features would it possess? Foundational stepping stones building upon NIST effort rather than recreating the wheel. Autonomous control, autonomous grid services with different needs. Energy service interface. Anticipated benefits. ESI allows sites that choose to participate in grid services a way to connect via consistent interface that creates service oriented architecture. Grid expresses service request. DERs decide how service is provided. Improves interoperable feature set. Standard interface permits grid communication to evolve independent of control in buildings. And it improves responsive loads and grid performances through network optimization, unambiguous communication, and transaction support that improves resilience, capacity, and intermittent resources integration. And it protects owners, assets, and controls service levels, enables open specifications used in buildings, codes, and standards, supports more open market competition among resources, and it improves utility DER procurement and reduces cost for implementing services. Distributed energy resource DER introduction. Increased demands on the nation's electrical power systems and incidences in, incidences of electricity shortages, power quality problems, rolling blackouts, and electricity price spikes have caused many utility customers to seek other sources of high quality, reliable electricity. Distribution energy resources DER small scale power generation sources located close to where electricity is used. Example, a home or business provide an alternative to or an enhancement of the traditional electric power grid. DER is a faster, less expensive option to the construction of large central power plants and high voltage transmission lines. They offer consumers the potential for lower cost, higher service reliability, high power quality, increased energy efficiency, and energy independence. The use of renewable distributed energy generation technologies and green power, such as wind, photovoltaic, geothermal, biomass, or hydroelectric power, can also provide a significant environmental benefit. DER taxonomy. Distributed energy resources DER are electric generation units typically in the range of 3 kilowatts to 50 megawatts located within the electric distribution system at or near the end user. They are parallel to the electric utility or stand-alone units. DER have been available for many years and are known by different names such as generators, backup generators, or on-site power systems. Within the electric industry, the terms that have been used include distributed generation (DG), distributed power (DP), and DER. Note that the use of DER in this resource page refers to the broadest range of technologies that can provide power to the user outside of the grid and includes demand side measures. Distributed generation. Any technology that produces power outside of the utility grid, example fuel cells, microturbines, and photovoltaics. Distributed power. Any technology that produces power or stores power, example batteries and flywheels. Distributed energy resources. Any technology that is included in DG and DP as well as demand side measures. Under this configuration, power can be sold back to the grid where permitted by regulation. Types of DER technologies. DER technologies consist primarily of energy generation and storage systems placed at or near the point of use. Distributed energy encompasses a range of technologies including fuel cells, microturbines, reciprocating engines, load reduction, and other energy management technologies. DER also involves power electronic interfaces as well as communications and control devices for efficient dispatch and operation of single generating units, multiple system packages, and aggregated blocks of power. The primary fuel for many distributed generation systems is natural gas, but hydrogen may well play an important role in the future. Renewable energy technologies such as solar electricity, biomass power, and wind turbines are also popular. Characteristics of DER. Some of the primary applications for DER include: first one, premium power, and reduce the frequency variations, voltage resistant transients, surges, dips, or other disruptions. Next one, backup power, used in the event of an outage as a backup to the electric grid. Peak shaving, the use of DER during times when electric use can and demand charges are high. Low cost energy, the use of DER as base load or primary power that is less expensive to produce locally than it is to purchase from the electric utility. Combined heat and power cogeneration increases the efficiency of on-site power generation by using the waste heat for existing thermal process. Applications, users of DER have different power needs. Hospitals need high reliability backup power and power quality premium power due to the sensitivity of equipment. Industrial plants typically have high energy bills, long production hours, and thermal processes, and would therefore seek DER applications that include low cost energy and combined heat and power. Computer data centers require steady, high quality, uninterrupted power, premium power. DER technologies are available now and are being developed to meet these needs. DER projects include a police station in New York Central Park bought a fuel cell to run its electronic crime fighting equipment, saving dollars 2 lakh over the cost of a line upgrade. The Shop and Save supermarket chain has installed base load generators at almost a dozen of its grocery stores, avoiding $40,000 in losses per day in the event of power outage. The Santa Rita jail in Dublin, California has an on-site photovoltaic system that produces 1.18 megawatts, giving $15 million in net savings over the 25-year life of the project. And that's the end of the topic of Tech Talk for engineering chemistry, and I presented the information here, and thank you.